Hello guys, so today we're going to be looking at Vieta's formulas. So Vieta's formulas are essentially a set of formulas that help us describe the relationships between the roots of some polynomials. And so before we begin looking at what they are and how they work, we first need to learn something that helps us build the foundation for that. And these are called elementary symmetric sums. So suppose we have some arbitrary polynomial p of x, and let's say the roots are going to be x1, x2, x3, and so on, all the way to xn. So that means p of x has degree n, and it has these n roots over here, because we know that p of x can only have a maximum of n roots. Now, what exactly are elementary symmetric sums, right? So I think it is easier for me to first show you a few examples. So typically we're going to use sk to denote the kth elementary symmetric sum. So this is like a really fancy way of saying it, I guess. Like normally you can just call it the symmetric sum. And so what does S1 look like? S1 is just going to be equal to the sum of all of the roots. And then what about S2? Well, S2 is going to be equal to the sum of all possible pairwise products of the roots. So imagine instead of adding each individual term together, you're going to group two roots together at a time, and then you're going to take their products, and then you're going to sum every single one of these paired products together. So it looks like this. And note here that I'm like sort of grouping x1 with x2, so this is going to be a product, and then x1 with x3, and then x1 with x4, and then so on, all the way to x1, xn. And then we're going to repeat with x2, x3, and then go on, and then eventually we're going to get to xn minus 1 and xn. This is going to be like the last pairwise product, right? So that's going to be S2. This is the second elementary symmetric sum. And then S3 is going to just be equal to, well, as you can guess, it's just going to be all triplets, and then all triplet products. So it's going to look like x1, x2, x3, plus x1, x2, x4, blah, 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 plus xn minus 2, xn minus 1, and xn. And this is going to be the last triplet wise. And then this is going to continue, right, until we reach Sn, which is just going to be equal to the product of all of them. And I guess you can see that how this kind of makes sense, right? So whatever the term S over here is, whatever the term K is over here in the subscript, that's just going to be equal to how many terms or how many roots are going to be in each grouping that's going to be multiplied together, right? So N means, Sn over here just means that there's going to be N roots together, multiplied together, and you're going to take the sum of all possible n groupings. But since it only has n roots, that means it's just going to be the product of every single one of them. So now that we sort of understand what elementary symmetric sums are, what are Vieta's formulas? So Vieta's formulas, right? So let us look at the same polynomial p of x again, and now we can assign some coefficients to the variables. So the coefficients are just going to be denoted by an over here, and then an minus 1. Right? And a0 is just the constant. So what exactly is Vieta's formulas? Well, I'm just going to write them down here. Okay, so you can see here that the first symmetric sum, which is S1, is just the sum of all the roots, right? And that is going to be equal to this term over here, this coefficient over here, divided by an over here. And And then we're also going to multiply this value by -1. And then the second symmetric sum is equal to an minus 2. So that is going to be the coefficient of the x to the power of n minus 2 term. And that's going to be divided by the leading coefficient over here, an. And then note how the negative sign is no longer there, which means this is just going to be the positive value. You don't need to multiply by -1. And then once again, once you get to S3, there's the negative is back. And then you take the coefficient of the x to the n minus 3 power. And then Sn finally at the end is just going to be equal to -1 to the power of n. So this depends on the degree. It depends on the degree of the polynomial, and it's going to be equal to the constant term over the leading coefficient. So you can see over here that the negative sign sort of just alternates, right? So from S1 to S2, the value gets multiplied by -1, I guess, if you can say. Like, there's a negative sign in S1 and then there's no longer a negative sign in S2. And this pattern is just gonna keep going on. And you can also notice how for each successive SK, like from S1 to S2 or to the next symmetric sum, like the numerator changes from the coefficient of the x to the k to the coefficient of the x to the k term. It changes from that to the coefficient of the x to the k minus 1 term, like an minus 1 over here, and then it goes to an minus 2, an minus 3, all the way to an minus n, which is just equal to a0. Yeah, so that's pretty much all there is to Vieta's formulas, and you can see that this can be applied to pretty much any sort of like quadratics, cubics, polynomials to any degree n that you want.